Alright, so we are getting started. This is the session of path and motion planning. I want to mention that we had some problems with the projector earlier, so if you still have problems, please stay with us. Our first paper is a journal paper presentation. So Bernhard will give the presentation of implicitly coordinated multi-agent pathfinding under destination uncertainty, success guarantees, and computational complexity. And this is the award for the longest title.
Yeah, thank you. You have to get some award. Yeah, now my time is over because the title is so long. No, but I guess I owe you to explain the title, right? So it has the phrase implicit coordination in it. What is that? Well, coordination can happen explicitly if you talk with people and then coordinate, for example, to go out of the way or work together, or it can be implicit, just by doing things. And when you look at distributed multi-agent planning, well, then implicitly coordination comes up very naturally. So when performing, when planning, we have to assume that the other agent fits into this plan, and we have to take the perspective of the other agent and plan from their perspective. And then the question is, how can you make sure that the joint execution of plans that are formed in this way are in the end successful? Here I have an example of an implicit coordination. Okay, so I think that is pretty impressive, in particular because this little kid couldn't talk already. So what do you think was happening there? I guess what was happening there that the kid, they did goal recognition, so it figured out that that the big guy wanted to put the papers into the cupboards, and then the kid adopted this goal. And finally, it made up a plan so that it was implicitly coordinated, namely opening the doors so that the other guy could put the papers in there. So this is at least my interpretation. So we can come up with mechanisms that do that as well? Well, perhaps. And we looked at it from a completely abstract point of view. Analyzing what's going to happen when you do epistemic planning. And we also looked at it from a more concrete point of view, so what's happening when you do multi-agent pathfinding. And that's a problem that comes up in a lot of applications. Well, be it that you're in a traffic situation, that you're in an airport or whatsoever. As computer scientists, we abstract away from all these little physical things, and look at it as a computer scientist. You can come up with this multi-agent pathfinding problem, which is sort of very easy to state, namely that you have a set of agents, you have an undirected simple graph, you have an initial state where the agents are placed on the nodes, and you have a goal state, which is modeled just by an injective function. And what you want to get is you want to get a sequence of movements that transforms the initial state into the goal state. So that's easy enough, without collisions, of course. And here we have a little example where we have a square robot and a circle robot, and they want to move to the respective destination, which are marked with little symbols here. So the circular robot might plan to go to V2, and then it arrived at its destination, but of course it wants to achieve the common goal, so it goes out of the way and allows the square robot to go to its destination. Finally, the circular robot also can go to its destination, and everybody's happy now. They have achieved their common goal. The point is that when you deal with this kind of problem, you usually create a central plan. That is, somebody from above looks at this problem, comes up with a good plan, and then it distributes this plan to the agents, and then they can execute it. And we want to generalize that. But before we generalize that, let's just state some facts about this problem from a computational point of view. The problem has been analyzed extensively. Deciding existence of a plan is a cubic problem. Deciding bounded existence, which means, well, that is the decision problem corresponding to the optimization problem, is NP-complete. And there are a number of optimal and suboptimal algorithms. Okay, that's something we have to remember because that comes up again in the talk. But now we generalize this thing. So first we say, what about if these plans are generated in a distributed fashion? So all agents have the same knowledge about the environment, the positions are all known, and now each agent generates a sequential plan containing own actions and actions of the others. So this is then an implicitly coordinated plan because, well, you hope that the other agents act according to what you have planned. Now, when you come to the point where you execute the plans, well, you have to say what a joint execution should look like. And, well, we defined it this way here. One agent who wants to act, so has one action as its first action in this plan, is chosen randomly, and the action then is executed. So this is sort of an asynchronous regime to execute this plan. And it's similar to what is happening when you play a real-time game, right? In a real-time game, the one who acts first is able to do what he wants to do. Well, after this execution of this action, then the agents that have not anticipated the action need to replan and come up with a better aligned plan. Okay, there's one good news now, and the good news is, well, agents can never end up in a dead end. Why is that? Well, because all agents always act according to a plan such that everybody can reach their destination. That's the good news. Okay, but of course things can go wrong. What can go wrong? A lot of things. So first of all, the agents could be lazy. That is, sometimes they choose a plan where they expect that another agent should act, although they themselves could act. All of you have experienced this situation before. Well, having had a dinner with your partner and then the dishes have to be done. Okay, everybody forms a plan, and these plans are also successful, and the plan consists of that the other one does the dishes. Okay, but unfortunately, then all the agents will wait forever. It's sort of like a deadlock, but well, we don't have resources here. So what can you do in order to avoid this situation? Well, you can require that the agents should be eager. So eager agents are those that introduce an action in their plan when they can, and then they start to execute it. There the problem is that agents might create cyclic executions, so they don't have cyclic plans, but they can create cyclic executions because, well, they do crazy things just to act. Here we have an example. We have, again, our two agents, and they want both to go right, and one of them is chosen, the square robot. And now, well, C, the circular robot, well, still can replan, and he plans also to go right. Looks crazy, but there's nothing against it. Well, he's following an eager policy or eager plan because, well, in the end he can go back and then go the other way around. Now, the square robot has to replan, and what does he do? Well, he plans to go back. And you can guess the circular robot also can now replan and plans to go back, and then they are in the same situation they were before. They have created a cycle in their execution, and that's something they can do again if the scheduling is bad. Okay, so what can we do about that? Well, the problem seems to be that these eager agents, they just act without caring about whether they create a shortest plan or not, whether they come closer to the goal. And so we introduced the notion of optimally eager agents that plan to act first, but only if this plan is an optimal plan. And then you get the guarantee that infinite executions aren't possible. And that's great. Why is that so? Well, the point is now, they might come up with the same plan. No, they might not come up with the same plan, but all the plans they come up with have the same length, right? And so if one of them now executes an action, and there will be one because they are all eager, then this action will be executed, everybody replans or uses the same plan, but these replanned plans will one step shorter. And well, then they converge, of course. Okay, so that works perfectly out, which means that in this case, implicit coordination works very well by observation and plan optimality. Okay, that's great. The only problem is, well, we have to solve now NP-hard problems. And as you remember in the beginning, the problem itself, forming a plan, is a cubic problem. Well, you get cubic length of cubic plans of cubic length, but you don't have to solve NP-hard problems. So can we do something about that? Well, maybe, but it doesn't seem to be the case. What we now want to do is we want to generalize things a little bit further, and this makes the problem really complicated because now we say, well, the destinations are not common knowledge among the agents anymore. So for each of the agents, we assume there exists a set of possible destinations, and this is common knowledge. I'll show you an example in a minute. The common goal of all agents is still that everybody reaches its destination. And well, in order to make sure that in the end everybody knows that they have reached the destination, we need to introduce what we call success announcement or shutdown notification. That is a message that is sent to everybody in order to note that the agents have arrived at the destination, and if everybody has sent this message, then everybody knows that the common goal is reached. This sort of models multi-robot interaction without communication, so could be in a factory when the Wi-Fi has broken down, and well, still the robots want to move. Now, how can they form an implicitly coordinated branching plan? Well, here we have a situation where agent S wants to go to V3 and knows that circle agent C wants to go to V1 or V4. Oops, sorry. And vice versa, C wants to go to V4 and knows that S wants to go to two particular places. Now let's assume that S forms a plan in which it moves in order to empower C to reach their common goal. Well, in order to do so, well, S needs to shift its perspective in order to plan for all possible destinations of C. And while doing that, S must forget about its own destination. So these are the building blocks we have for our branching plans that we are now forming. These are movement actions, success announcements, perspective shifts, and then the branching or not unconditional continuation. This is an example for such a branching plan. So here we start with S moving from V1 to V4, and then we have a perspective shift to C, and depending on what is happening, on what the destination of C is, V1 or V4, we form a different plan. And then this goes down. And in the end, well, everybody has reached their destination and has made a success announcement, and that holds for all possible destinations. So in order to then say what a successful plan is, we borrowed from non-deterministic planning and say that these plans should be cycle-free, successful, and covering. Well, when we find such a plan, it's I-solvable. And a crucial step in solving or creating these plans are so-called stepping stones. We call stepping stones. These stepping stones are situations where agent I is in a state in which it can move to all its possible destination, announcing success, and afterwards, for each of the possible destination, the resulting instance is still I-solvable. Here we have an example. So S can create a stepping stone for C by moving to V3. So now the circular robot can move to all its possible destination, V1 or V4. And then with that, the circular robot has created a stepping stone for the circular for S, and it can move to all its possible destination, and we are done. Now, the interesting point is that, well, when you generate such a plan, then it is enough to generate plans which just have branching points where you utilize stepping stones. And here we have the proof sketch. Here we have a proof by example, and the example is, well, here we have a situation where we don't have a stepping stone. Here we don't have a success announcement. Well, that means that further down we need to have stepping stones if we don't have it here. And that means we can cut away this point here, and then we end up with plans that only have branches when they are stepping stones utilization, which means that when you look at the execution costs of such plans, which are just the number of atomic actions in the longest branch, then you can bound them by a polynomial bound, which just comes from the fact, well, that you have only linearly many stepping stones, and then in between them only cubic many movements. So now we can look at can we solve these problems as before, and it turns out that this is not possible. So the optimally eager agents, they still can run into execution cycles. We have to introduce a new notion like what we call conservatism, which just means it's a policy that is history dependent, and that means that we have the already executed action as a plan prefix. If we put that together with polynomial with optimally eagerness, then we get the theorem that joint execution and replanning by conservative optimally eager agents is always successful, and the execution cost is polynomially bounded. Of course, when you restrict the number of agents, first of all, when you look at the complexity, then it's p-space complete, and if you restrict the number of agents, then you get a polynomial result, which brings me to the summary of 1 minute over or something, or 2 minutes over. So what I've shown you is that the MapF and the MapF with destination uncertainty generalize the MapF problem, dropping the assumptions that plans can be communicated and that destinations are common knowledge. Joint execution of implicitly coordinated plans can be guaranteed to be successful and polynomially bounded. MapF problem, MapF bounded plan existence is NP-complete, and bounded plan existence for the problem with destination uncertainty is p-space complete. Well, the take-home messages are, if you want to do implicit coordination, then that works in our frameworks. And the second take-home message is, if it's possible to communicate, then do it. That can save you an awful lot of hassle, in particular in our case, computation. Thank you. Yeah.
Do I understand you're making the assumption that only one agent moves at a time?
Yes.
Well, that seems an unusual one.
Well, it's what Kornhauser did, right? And of course, we are looking for doing that for parallel execution. But then implicit coordination has to be redefined in a, we haven't any idea how to do that yet. Okay.
Thanks for the talk. I was wondering about the final take-home message. You should communicate whenever possible. Do you think this framework could be useful in settings where you can communicate, but only a limited amount of times, for example, or the cost of communication is high and you need to optimize for that or something?
That's also one of the things we would like to look into it. So we have now the extreme of not communicating and the other one where you can, where you communicate your plans. So is there space between there, and well, can you make use of it? Yeah.
Thank you very much again.
Let's see, is it? Cool. Okay, so I'm Graeme, and this is some work that I've been doing with Daniel Harabor, who is sitting right there, and Peter Stuckey over at Monash University in Australia. And this came about because I come from an optimization background. I do constraint programming. And then I made the mistake of having some conversations with pathfinders. And it turned out that the problem structures that we work with have quite a lot of similarities. So the problem we're looking at is, as with the previous talk, multi-agent pathfinding. But we're in a sort of a more restricted class of problems where we have synchronous time steps. Everything's a global plan. So we just have a set of agents, each of which have their goal, or their origin and goal locations. And what we want is a common plan that gets every one of them to their goal locations without any of them passing through one another. And so the normal objective functions are either make span or sum of costs, and I'll talk about that in a little bit, but really it's just some function of the costs of each of the agent's plans, right? And so what is a conflict? Conflict happens when two agents try to occupy the same vertex or to pass through an edge. So we usually assume that the map that we're navigating in, the space we're navigating in is a graph, right? So we have unit costs and unit time, and I'll talk about generalizations possibly later. But so how do we solve these? There's a bunch of different ways that people use to solve these coordination problems, and the one that we're building on is called conflict-based search. Now in conflict-based search, it's an optimistic algorithm. So we assume that our graph is sparse, there's little contention, so we just plan each of our agents independently. And then at the end, we'll discover that, sure enough, the purple agent and the yellow agent, in their individual plans, if we try and run it, they end up occupying the same vertex. And so what CBS does is they plan independently, and then you check the candidate plan, and if there's a conflict, we decide which agent has priority at that location time pair. And then we're going to branch. So in this case, we've decided that, well, the purple agent is going to go straight through, and so the yellow agent is going to have to wait. But of course, that's not the only choice we could have made, right? We could have said, well, the yellow agent gets that priority, and so the purple agent is going to have to wait. But in either case, one of those two agents has to take a wait somewhere, right? Now, since this is branching, we need some way to, and we're interested in optimal search, we need some way to explore the space of possible conflict resolutions. Right now, in CBS, the usual way that people do this is using A star. So they use A star at the low level to route individual agents, then they use A star at the high level to explore the space of possible conflict resolutions and try and find the best path. So your heuristic value at a high level node is a lower bound on the number of weights that agents collectively have to take in the overall feasible plan, right? Now, the problem is, so if we do this in CBS, we're going to see that there's a conflict between the purple and the yellow agents. I apologize if that is illegible. So what we have written there is that on the left-hand side, we have the purple agent cannot be at location U at time 1. U being the top left cell that should have been marked. And so in both of, and on the right-hand side, we have the prioritization the other way. And in either case, our lower bound of 0 has been promoted to a lower bound of 1. Because on the left side, one agent had to wait, on the other side, the other one had to wait. And then we look at the resulting plans in the node that we expand, say the left one. But we discover there's still a conflict that remains between the blue agent and the green agent, right? Because that was there in the original plan. It hasn't been resolved by our resolution. So now we have to resolve that one. And so after expanding the left node, both of those children have a heuristic value of 2. But we still have an unexpanded node that looks great, right? That is the one on the right. But if we were to expand that, we would see that, sure enough, the blue and green agents still have a conflict. And so we're going to have to re-expand the conflict we just resolved in order to prove that the cost bound that we've got is the best we can find. Man, that's not super great. Where are we? There we are. Right. So why does this happen? Well, the problem is that A star doesn't have any way of knowing that the inferences that it made on the left-hand side are still totally applicable to the right-hand side, right? Once it picks the right child instead of the left child, the entire universe might have changed. We can't make any assumptions that weren't already sort of encoded in our state previously. But as I said before, I come from a constrained programming SAT background, and we've spent a lot of time doing stuff with search trees. Right, and this looks an awful lot like a search tree. Now, the way that we do this in modern lazy clause generation solvers is that we just stole ideas from SAT. Right? So in SAT, they, again, have the same sort of structure. And so they just do conflict analysis. So whenever you go down a branch and you find a failure, you then do some reasoning about the sequence of inferences that you made to try and figure out a minimum subset of the things that happened that were enough to cause your failure. Then you add that to a database, remember it, and remember not to do that again, right? And since I'm keen to borrow ideas wherever I can find them, I thought, well, what happens if we try and apply this to multi-agent pathfinding? So we take CBS, but instead of using an A-star search for our high-level search, we're just going to use a lazy clause generation CP solver. We'll swap it out, plug in conflict analysis, and hopefully everything will magically be OK. So what we're going to do is we're going to sort of start off, as with CBS, with no assumptions in our model. We're going to assume that there's no conflict, so we'll just run all of our pathfinders optimistically. But what we are going to do is introduce a variable for each agent that encodes the value of its path, which is how we're going to run our search for the optimal plan. Right? And like in CBS, where we have our conflicts that we decide on, in our underlying CP model, we're going to introduce these, what we call permitted variables. So in CBS, you block a single agent from a given location time. Here we just have a decision variable that we add to our CP solver, where the CP will search on to decide who gets that location at that time. Right? And so when we build up our model, we have a propagator for each agent that ties these two things together. Right? So every time the solver searches on one of these permitted variables and says, well, the agent 1 is removed from the domain of this location, it's going to update, rerun the pathfinder for that agent, and update the lower bound on the path length. And then we have however we encode our objective. Right? I'll talk about that in a little bit, but we just have some function of our cost variables that tell us what the cost of the overall plan is. So what we're going to do, we're going to initially constrain our cost variables. We're going to try and generate a plan. If we see a conflict, we add a new variable to the solver, hook it up to the propagators, generate a new candidate plan, and repeat. If at some point the solver, the propagators update the cost. And if at some point the solver fails, we say, well, given the conflicts that we know about, there is no feasible solution under the costs that we've assumed. It'll then do explanation to go, OK, given the decisions that I've made based on the permitted variables, which of those were actually relevant to the conflict that I saw? Now, in order to do this, we need a CP solver with a lot of special things. We need to be able to add variables at runtime. We need to be able to add propagators that do explanation. we need to do some fancy things with assumptions. Fortunately, I prepared one earlier, so I could just use that one. So if we have a small example, so this is just two agents. They're trying to get through a fairly narrow corridor. So what does this look like? Initially, we have no constraints. We've got two variables. Our path lengths, we've fixed the upper bound to 9. But until the propagators run, we don't know anything. And then we just run our low-level pathfinder for each one. So we run pathfinder for C1 and discover that the lower bound of the cost is 9. And C2, we run it, and again, the shortest path is 9. And we check our plan, right? Our plan, unfortunately, has a conflict in it. So we're going to go and introduce a new variable to our solver and say, OK, solver, you need to decide who gets this location. And so then we're going to call the solver and just run it until it finds the solution that it thinks is feasible. And so it's going to branch and say it picks agent 1 gets that location. So that then is then going to put an obstacle into the map for agent 2, right? Because it's no longer allowed to use that location. That's going to force us to rerun that pathfinder. And the shortest path is for it to take a wait somewhere along there before it goes through location U. Right? Now, because we're doing explanation, we discover that that means that the path length is at least 10. And our minimal explanation, now in general, it won't always be the case that every obstacle is relevant to this bound. But in this case, the one obstacle is the thing that was needed. So anytime location U is not allocated to agent 2 at time 5, it has to take at least one wait. And that's violating our bound for the cost of agent 2. So we're going to have to backtrack. And then that new constraint is going to fire. And it's going to force permitted U5 to be equal to 2. It says that agent 2 has to get this location. Unfortunately, that's going to force us to rerun agent 2's pathfinder and find that, well, the new shortest path for agent 2 is going to be at least 10, which also violates our constraint. And we generate a new clause that encodes that information. And so now we have a constraint that says that, well, if we allocate U to agent 2, then agent 2's cost is at least 10. If we allocate it to agent 1, if we don't allocate it to agent 1, then agent 1 is at least 10, which means that we have no feasible solution. We know that either agent 1 has to take a wait or agent 2 has to take a wait, right? And so that means that our cost bound is no longer feasible. Now, the important thing is everything we've learned is independent of any other agents that are in the map. Like if there are a bunch of other agents, hundreds of other agents that were on the map, it doesn't matter. These things we've learned are sound, which means that they get reused even once we've moved on to other agents. Right. So if we restricted our concern to make-span objectives, then that's enough, right? We go, OK, we pick the longest path length that is our make-span bound. We constrain every agent to that bound. We then try and generate a feasible solution. If at any point we fail, then that's an indication that our make-span is not big enough. And so we just increase it and keep going. And in fact, the no good we get back tells us how much the solver thinks we should increase our bound by. But make-span is fine, but sum of costs is where it's at. That's what people care about. Now, all of the SAT-based methods for pathfinding usually restrict themselves to make-spans. And the reason for that is that CP and SAT solvers are not very good at adding things up and proving optimality, right? If we have a simple problem here where we have the sum of x1 to xn and y1 to yn, we have this constraint on the side that says that for every x and y, at least one of them has to be 1. If I throw this into a CP solver, it will probably solve for 10. If I wait a couple minutes, it'll solve for 15. If I have n equals 20, I'll be waiting basically forever. Because if I just throw that into a CP solver and run it, it's going to take an exponential number of no-goods to actually prove that optimality. Now, the reason this fails is because it doesn't have a name for the term x plus y. Right? For every x variable, there's some plan that has it at its minimum value. and for every y variable, there's some solution that has its minimum value. But collectively, they're infeasible. So again, with my theme of stealing ideas from other areas, they've run into this problem in MaxStat solvers. And the approach that they use is, well, one of the approaches they use is called core-driven optimization. Now, the particular version that I'm borrowing from is called OLL, where you basically just start off optimistically assuming everything takes its best value, and then you progressively see whether that's feasible, and if not, you extract a subset of those that are were sufficient for its feasibility and gradually reformulate your objective. So what does this look like in our case? So we start off with a bound of 44 because each of our agents has a shortest path of 11, and then we run our solver, find some conflicts, and we get a call that says that, well, either agent 1 or agent 2 has to take a weight of at least 1. And so the trick is we're now going to restructure our problem a bit. We're going to relax the bounds on agent 1 and agent 2 to 12, so both of them are allowed to take a weight. But we have a new variable z1, which is the number of those agents who have taken a weight. And we constrain that value to be 1. Right? So we've now increased our bound to 45, because we know that at least one of them has a weight. We've priced that in, and now we've reformulated our objective so that we're only constraining the remaining cost. And so then we try and solve again. We find that there is a solution to the subproblem for agent 1 and 2, right? Where, say, agent 1 takes path 12, agent 2 takes cost 11, and so then that z1 term is going to be 1. But there's still a conflict between agents 3 and 4. And we repeat the same process, we update our bound, and we find a feasible solution of cost 46. Right? Now we've implemented this. We tested it against CBS, just a bog standard CBS implementation, CBSH, which as of about 12 months ago was the state-of-the-art implementation. It's been a busy year for multi-agent pathfinding. So in the case of 20 by 20 grids with 10% obstacles, our results are pretty good, right? Here we have the orange line is CBSH, the current or the previous best CBS implementation, and red line is lazy CBS. So it's doing all right. For game maps, things get a bit trickier, but we're still doing pretty well. Right? There's a substantial increase in success rates. So our setting is 50 sets of random start destination pairs and a 5-minute timeout. So we'll talk about that in a second, but for one thing, it's available. If you want to play around with it, you can. It's on Bitbucket. If you want to use the CP library by itself, you can also do that too. So we have these state-of-the-art results. An important point is that there's no MapF-specific heuristics in there. Right? All we're doing is I'm just using the default activity-directed search heuristic. There's no dedicated reasoning other than the propagators. There's lots of stuff to do. So the current implementation is restricted to 4 connected grids with unit costs, but for the most part, it could be changed without changing anything. And the nice thing is that a lot of the improvements to MapF solvers can be applied directly. And just as a sneak peek, we had that previous slide that I showed. And so if we steal some rectangle-based symmetry breaking for these problems, we get the purple line on top. Now that green line is a suboptimal solver. So we're actually proving optimality more reliably than a basic eCBS implementation with 1% obstacles. OK, thanks for your attention. That is all.
I think this is really cool. Any questions?
Thank you for a nice presentation. I think it works. Oh, it does. OK.
Yeah.
I was wondering, in your constraint programming formulation, what is the constraint that detects the inconsistencies?
That is a dedicated propagator. So I just have a propagator that runs a single agent A-style search on the time-expanded graph. and propagates the upper bound, you never get infeasibility independent of the bound because all obstacles are transient. That's another extension we're looking at. Yeah.
Any more questions? So I was wondering, I mean, there have to be sort of some trade-offs, right? If you put this into CDS, you need to change CDS in some ways.
So I'm not really sure how you would go about adapting. Like, the big change is the alteration of the high-level search. Right here, we're doing a sort of failure-driven, failure-driven optimization process rather than A**'s best first state exploration. So it's very, very depth first. It's iterated depth first, but it's depth first. And I'm not sure what it would mean to try and adapt these techniques to that high-level solver. Sorry, yeah.
Fair enough.
Yep.
Okay, thank you very much again. Our next talk is a short paper. It's on improving the combination of jump point search in geometric containers, and Daniel Harabor will give the talk.
G'day. My name is Daniel Harabor. Full screen. I'm from Monash University. This is joint work with Yue Hu, Long Qin, Quanjun Yung. Please don't do that. Quanjun Yin and Cong Hu. So they are from the National Defense University in China. So the theme of the session continues, pathfinding. We saw the previous session was a simplification of the first talk. Here we have a further simplification from multiple agents to single agent search. And so what I want to talk to you specifically about is grid-based pathfinding. So this is a very popular application area with video game developers. And the topic of this particular talk is focused specifically on improving pathfinding, single agent pathfinding search, especially in the context of video games. But of course, the results are more generally applicable. So the kinds of video games that I'm interested in are things like this. This is Company of Heroes. I was not involved with this. So what's happening here is there's lots of agents that are moving around, and we need paths for all of them. But unfortunately, what happens with AI developers is they're very resource poor. They tend to get a very small amount of memory and a very small amount of available CPU, so we need to compute paths very, very fast. More than that, though, the paths need to be intelligent looking. So, we would like to compute the best path possible. So the world here is represented as a grid. I assume it's an 8-connected grid. I assume the standard cost model, straight steps cost 1, diagonal steps cost 2, cost square root 2. So let me tell you about some leading algorithms in this area. So here are some results from the 2014 Grid-Based Path Planning Competition, 2013 and 2014 editions, actually. And so what I want you to focus on is the query times. So these are in microseconds, right? So you can see that because of the competition, times have gone way down. Averages are around 145 microseconds, which is great. So that was for the winner in 2014, an algorithm called SRC. Storage is gigantic, 52 gigabytes for 132 maps. Preparation time is gigantic, 200 hours. Good news is, a couple of years later, Nathan Sturtevant and Steve Rubin, who works in video games, were able to substantially improve the pre-processing costs. So they describe an algorithm called JPS plus BB. And so the nice thing about JPS plus BB, as compared to the previous 2014 path planning winner, is you get very similar query times on average. The storage is much, much smaller. And the preparation time is a few factors reduced. In this work, I want to tell you how we further improve on this algorithm, JPS plus BB. We specifically focus on improving the pre-processing, but as you'll see, we also improve the query time performance. Okay. Very briefly, I need to tell you what JPS plus BB does. The secret ingredients are two. The first one is symmetry breaking, and the second one is goal-directed edge pruning. The way the JPS plus BB does symmetry breaking is it builds on a previous algorithm from 2011 called jump point search. Jump point search, I guess, is most easily understood as a recursively applied neighbor pruning strategy. So if we take the node on the left and we look at its immediate neighborhood, the arrow indicates the direction of travel from the parent to the node. Well, all of the nodes that I've marked here in gray are ones that we can better reach from the parent than going from the parent to the node and then to the successor. So we can just prune them all. Okay? And there's only one successor remaining. So that's really nice, right? We've substantially reduced the branching factor with this strategy. When we move diagonally, we can reduce the branching factor again, but this time not quite to 1. We have 3 successors. You see here on the right, obstacles. So normally we would try to prune the 2 neighbors down the bottom, but because of the obstacle, we have to consider them. So obstacles force us to consider additional neighbors, and we branch. All right. I don't want to tell you too much about the mechanics of JPS. If you're interested, please read the paper. What I want to show you is what JPS looks like if we run it as a Dijkstra search. So what it's doing is it's actually applying a canonical ordering, where every node on the map is reached by a path where diagonal moves appear first. Okay? So what I've shown here is how the path to every node looks like from this designated starting location. Okay? And so you can see that in some directions, we have a single series of successes, which we can easily prune. So JPS is a recursively applied pruning strategy. All of these things that I've marked here dashed, so these are all recursive traces of jump point search where they don't lead anywhere. In fact, the only interesting nodes on this map are these purple nodes, right? These are the ones that help us to bend around obstacles in optimal ways, right? That's really what JPS is doing. It's symmetry breaking, and the only interesting nodes are these things called jump points that are helping us to bend optimally using a canonical path. The final ingredients of JPS is entirely online, but all of these pruning, all of these recursion, we can actually pre-process. So we can store some information with the source node to say, well, if you go above, you can travel 3 steps, but then you reach an obstacle. And that's what this -3 means, right? That it's an obstacle. Travel 3 steps, but then it's an obstacle. So if it's a black number, we have a jump point at that location. The second part of JPS plus BB that's interesting is called geometric containers. So here, the idea is very, very simple. We run Dijkstra from every source, and we record what are the reachable nodes that we can optimally reach from every edge. So if we take this diagonal edge here, well, I've marked in green all of the nodes. So we can just put a bounding box around this, and we can query, is the target inside this bounding box? If it is, that's great, we need that edge. If it's not, we can throw that edge away during pruning. So that's JPS plus BB. And it's very, very fast, right? Here, it marches directly to the target. So it's extremely fast, but very lengthy pre-computes. All right. So 2 very simple ideas for improving JPS plus BB. Instead of running Dijkstra search from every single node in the graph, instead we propose to run it just from the set of jump points. I've marked all of the jump points here. You can see that it's much, much smaller than a number of cells. So we get much, much better pre-computation performance. The other interesting thing that we do is we improve the online performance of jump point search, of a JPS plus BB. So normally JPS plus BB would go from the start, it would jump to the node B, then to D, then to G. We say, well, these are not very interesting. The only reason to stop at B is to go to C. So let's just recurse over these, and we'll collect C, E, and F as successors of S. But we can do a little bit better here by noticing that there is no point traveling beyond D, right? So beyond D, we can't reach the target anymore. So we can just stop. So we don't need to consider nodes like H, which would otherwise need to be evaluated. We have to test is a target inside its bounding box. Let me show you some results. So this is a bigger set of maps than the ones at the competition. And the new method is on the right. The original one is on the left. You can see that, for instance, in the case of StarCraft, pre-processing time goes down from 99 hours to process 75 maps to 11 hours, right? Space goes from just under 1.2 gigabytes to 65 megabytes, right? Big, big savings. 2 orders of magnitude savings in some cases. In case of the online search, again, we see 30–40% improvement due to this expansion strategy that I just described to you a moment ago. Okay, so we have here in microseconds the running time of the old method and the new method, and nodes generated, nodes expanded. So let me just wrap up because I'm out of time. So path planners often use lengthy all pairs precomputes in order to achieve fast performance. But the computed data isn't always reusable, right? We saw that really it was just a subset of nodes that was giving us most of the power of these search techniques. So maybe we can think about identifying these kinds of subsets, right? Jump point analogs for other types of graphs, not just grids. And thinking about these ideas not just in the context of bounding boxes, but other stronger things like compressed path databases, which prune much more aggressively than geometric containers. That's it.
I'll get started. I mean, bounding boxes are often sort of crude approximations, right, of the shape that you really want. You could think about better approximations, but then it's more time-consuming to figure out, what a point is within that shape. Have you thought about this? Would this make sense, to go to sort of better approximations, or is this the sweet spot?
So right at the end there, I mentioned other kinds of pruning methods. They use all pairs. So compressed path databases, you can see as going to the extreme of what bounding boxes are trying to do. They capture exactly which is the optimal move from the source to the target. And they have exactly the same pre-computational cost as computing geometric containers. So one of the current things that we're looking at is, well, can we actually throw out geometric containers and replace them with CPDs that are computed just for the set of jump points, which is a much, much smaller set. So now CPDs are normally just purely database driven. Now we can do a hybrid, right, which is partly database driven and partly search.
CPDs also need more memory, right, than bounding boxes.
Yeah, but the CPDs for the set of jump points is much, much smaller than we would normally store for the full CPD. So maybe we use a little bit more memory than bounding boxes, but hopefully we improve performance quite a bit.
There will be a talk later on today about CPDs, and we show additional improvements for memory.
Please come to the talk.
Good, so thank you very much.
Okay. Okay, I'm sorry about that. So I'm Takeshi Takahashi from University of Massachusetts Amherst. Today I'll be presenting a paper, Learning Heuristic Functions for Mobile Robot Path Planning using a Deep Neural Network. So I worked with Thorsten, Dr. Tian, and Dr. Wang when I was interning at Mitsubishi Electric Research Laboratories last summer. So efficient path planning is required in many applications like self-driving cars and home service robot. And the sampling-based approach, efficiency of the sampling-based approach depends on how good heuristic function you have. So by the way, I have a 4-year-old kid. And whenever he has baseball bat, everything in the room looks like a ball. So he's hitting around everything and he's breaking everything. So actually same thing happens to some people, including me. Now we have a hammer called deep learning. So every problem in the world looks like a nail. And then we are trying to hit every problem using that hammer called deep learning. So actually, I did it. For example, you can take some end-to-end approach using deep learning to learn mapping function from state to action space. So in this case, this is just my toy project. I take the imputation learning approach to learn how to drive in the simulator. So in this case, testing road and then training road are exactly the same. So it drives very, very beautifully. So however, once you change the environment, it doesn't work well. So this is kind of problem of end-to-end approach. Even you look at the state-of-art approach, according to what they say, their approach is still far from the real robot application. So in this work, instead of learning everything, I still use deep learning, but I try to use deep learning to learn heuristic functions. Then after that, we can use some reliable path planner. So the contribution of the paper is we investigated how we can use neural network to learn good heuristics. And then we applied the deep learning architecture commonly used in semantic segmentation. And then also we found out that choosing loss is crucial in this application. So our main focus is this loss functions. So we proposed some defined loss functions. And then we showed the land heuristics actually can reduce search cost during the planning in the small two domains. One is 2D grid world, another one is a continuous domain. Both of them are in simulation. So our task is we want to find a path from start state to goal state. And then our research question is how can we use neural network to learn good heuristics to reduce the search cost. So we don't care much about optimality in this paper. We care about the search cost. This means that we want to reduce the number of expanded nodes during the search. So our architecture is as follows. So this is our input space. Input to the neural network is a map, 2D map. And then we use some tensor or matrix to represent a goal location or goal pose. And then we use this as an input to the neural network. We use UNet structure. The structure itself is actually not that important. So if you're interested in, please look at the paper. And then it generates some heuristics over the entire space. And then we use this random heuristics with goal location and start location, and then we get a path. And then what we want to do is we want to reduce the search cost. So this is evaluative feedback. So you can formulate this as optimization problem or reinforcement learning problem. But in that case, it has a lot of difficulty. I believe path planner itself is not differentiable. So instead, in this case, we can prepare instructive feedback. Like it takes some time, but we create optimal heuristics or good heuristics. And then we compute the loss, and then back propagate, and we can update the neural network. However, in this case, again, our final goal is to reduce the search cost. And then we want to reduce that problem to supervised learning problem. So in order to reduce the reinforcement learning problem to supervised learning problem, you need to satisfy certain condition. I mean, those function has to satisfy certain condition. But if we use standard loss functions for regression problems like mean squared error or mean absolute error, it doesn't satisfy the condition. That means that still, if you get the lower loss, it improves the neural network, but a lower loss does not necessarily indicate better performance. So that's why we investigated loss function, and then we consider some some loss functions. First one is we consider the gradient of heuristic. So when you train a neural network, you use a gradient of loss, but in this case, we first compute the gradient of heuristic. So we apply some convolutional kernel, KA, that includes some robot dynamics and kinematics, and then compute the gradient of heuristics. So the concept is very similar to computing the gradient of the image using Sobel-Feldman operator. So in this example, in order to get the gradient of the x direction, that is the middle one, and the rightmost image shows the gradient of the image with respect to y-axis. Similarly, we take the gradient of the heuristic with respect to each action, and then compute the loss. So next loss function we consider is piecewise mean absolute loss. The heuristic values we want to have should be within lower bound of the heuristic and then optimal heuristic. So we can penalize heuristics based on its value. For example, the first term represents the heuristics that is lower than lower bound of the heuristic. The right figure shows the x direction is heuristic value, the y is loss. So if the heuristic is this region, you can penalize more. In the end, actually this part is not important, so you don't have to penalize, but if you want to penalize, you can penalize in a different way. And if your heuristic value is within lower bound and optimal heuristic, you don't need to penalize. The important thing is here. If your heuristic value is greater than optimal heuristic, it's better to penalize more. So I say I don't care much about optimality here, but it seems if we try to make the heuristic which is admissible, it helps the planner to reduce the search cost. So the two loss functions I showed is kind of handcrafted loss. So whenever we hear handcrafted, especially whenever I hear handcrafted loss, what we want to do is we can try another neural network to learn loss function. So what I did is I used Western generative adversarial network. So origin again is, so we have two neural network, generator, which is the neural network which generates heuristics, and then we have another network which is discriminator. So in the original work, Gange is trying to make a realistic image, and then a discriminator tries to differentiate a fake image and the real image. So these two networks compete each other to improve the performance. In the similar way, given some input to our heuristic function, it generates some heuristic, and given the round heuristic and the goal, this discriminator tries to differentiate round heuristic and then target heuristic. So this, when we train the loss, the discriminator, which is the same as original WGAN paper, and then when we compute the loss to train our heuristic function or generator or unit, the loss will be the sum of the normal standard loss, like mean absolute error, mean squared error, plus the loss of gradient heuristic. You don't need to use it, but you can use it, plus the loss from this double Gange structure. So in order to test this, our network structure and then loss function, we worked on two domains. First domain is this 2D grid world domain. So agent can go up, left, right, down, and then we use A star. So this environment is still small, and then 32 by 32 occupancy map. And then we try to randomize the map as much as possible. So we create a map based on 6 different types of map, but we randomly add also small noise. We randomly add the structure. And then also we randomly change the goal position, starting position, and created 180,000 training samples and then 10,000 testing samples. And then as a comparison, we compare the round heuristics against baseline heuristics, Manhattan distance, and then also we use scaled Manhattan distance. Once you multiply certain constant to Manhattan distance, it doesn't hold optimality anymore, but you can reduce a lot of search cost. And then in order to do the fair comparison, I consider the difficulty of the task, which is the ratio of the optimal heuristic at the starting position, and then baseline heuristic at the starting position. That means that if this value is close to 1, the task is easy because Manhattan distance already have some good value as a heuristics, and if this value is bigger, the task is more difficult. Again, we compare the number of expanded nodes during the search. And then, so this is the result. Top figures shows the results from the baseline. So green stars represent the expanded nodes, and then bottom figures represent round heuristic, or actually actual output of the neural network, except for red line and green stars. So as you can see, once you learn it, you don't have to expand a lot of nodes. And then, so rightmost image shows the task where there is no path between the goal and the start, so that our neural network generates very high values around the starting area. Starting area is the circle. Circle is the starting position. So that indicates that there is no path from the start point and then goal point. And of course, there are failure cases. And if you are interested in, please look at my paper for failure cases. So I extracted some results from the paper. So left figure shows the results from when the difficult level is 1.0 to 1.2, means that the tasks are kind of easy. This is the ratio of expanded nodes, so lower is better. And as you can see, in the case of an easy task, actually baseline is much better. You don't have to use neural network to actually create a heuristic if the tasks are always easy. But once the tasks are more difficult, neural network produce better result or reduce the search cost. And then if you train a neural network with the standard loss function, it's okay, but it doesn't produce better results compared to the neural network trained with our suggested loss functions. So I tried some combination of the loss functions, and then almost all of them works similarly. And in the case of double Gange, it looks fancy, but even though it takes a lot of time to train a double Gange, because we have 2 neural networks, it takes a lot of time to train the neural network, but we didn't get much benefit. So for the next domain, for that reason, we didn't use a double Gange, although we thought it was a good idea, but we didn't have much benefit of using a neural network to learn the loss function in this case. So in the next case, it's continuous domain. It's simulated, still simulated world, but we consider the 4-wheeled robot. The robot follows the bicycle models, and then we consider the 10 different steering angles, 5 for the forward direction, 5 angles for backward direction. We use a hybrid A star, so it needs to discretize the continuous space. So it doesn't have any optimality or completeness, but the paths generated by hybrid A stars are always drivable. And then we worked on some parking lot environment, and we randomized the occupied parking slots. Again, we randomized the goal and the starting positions. And in this case, we compare our learned heuristic against Euclidean distance, and they scale the Euclidean distance. So in this case, use of a difficulty level is hard because hybrid A star doesn't have any optimality anymore. So we just count the number of tasks where the learned heuristics are better than baseline heuristics. So left one is comparison against Euclidean distance. So basically, if you have more orange region, it's better. So in this case, if you compare the very basic baseline, the learned heuristics are better. However, once you compare it against scaled Euclidean distance, if you apply neural network naively, actually, you cannot beat it. So this is scaled Euclidean distance is still simple baseline, but if you apply the neural network naively, it cannot beat it. So in this case, if you use piecewise loss function, actually neural network is better than this baseline heuristic. So I confirm there is a statistical significance between them. So as a conclusion, we propose a new approach to learn heuristic function. And then the important thing is the loss function. Depending on the loss function, you can get much better results or much lower results. So you need to focus on loss functions if you want to train to learn heuristic functions. And then our preliminary results shows that neural network can reduce the search cost in many scenarios. And the good thing about the combination of neural network and existing path planning is even when neural network produces bad heuristics, path planner can still find a path many times. But in the case of end-to-end approach, this is not always the case. So as future work, again, we worked on very small environment, so we want to investigate the scalability of this approach. And then another thing is partially observable environment. The good thing about the neural network is feed-forward computation is pretty fast. So every time you get some information about the environment, you can recompute the heuristic functions. And then if the dynamic objects exist in some environment, we probably need to think about the structure of the neural network or more. So these are the two things we want to investigate more. That's all. Thank you.
Thank you.